Okay, we're back. Now we're going to be entering 11.4 over what are called comparison tests. The idea here is now that we know a few rules for certain types of series and whether or not they converge or diverge, we can use these comparisons, these different types of comparisons, to determine the behavior of other series that are in some way similar to the known types of series. All right, so to remind you, the two big types of series that we know the answer for now are geometric series. Let me keep it in simple form here. So geometric these are basically sums where the terms are exponential expressions, a number r raised to the variable in power. And we know these are convergent if the absolute value of r is less than 1, and it's divergent if the absolute value of r is greater than or equal to 1. And for those, for the convergent geometric series, we also we also know the sum, the value of the sum, by a formula that we talked about already. But then from the previous section, the integral test, we were able to determine the behavior of p series. These are series of the form 1 over n to the p, where p is some number. And I guess now we need to start with n equals 1. These p series are convergent if p is greater than 1, and divergent if p is less than or equal to 1. So we were able to prove that with the integral test. All right. So these, we can tell if it's of this type, we can tell does it converge or diverge. But if it converges, we aren't able to calculate its value. But like I said before, for most of these tests, the question will just be, can we determine whether or not a series converges or diverges? For the most part, we won't be able to calculate their values. So what we are doing is trying to compare more complicated series to one of the two types that I just wrote. And we've got two main types of comparisons. There's the regular comparison test, which says, suppose I have two series, summation an and summation bn, where all the terms an and bn are all positive. Let me say it like this. So the a's and the b's are all positive, but moreover the b's are bigger than the a's. So this is true for all n. Then there are two possibilities, or two useful comparisons. So basically, if the terms of the A series are all less than the terms of the B series, then this sum, informally, we can say this sum will be less than this sum. So, if the summation of the B's is convergent, that means there's a finite answer for the bigger sum. That means the smaller sum also has to have a finite answer. So the idea would be, if the summation of the a's is an unknown series that I'm trying to figure out the answer for it, if I can find a bigger series that I know is convergent, that means my unknown series is convergent. Similarly, if I know already that the summation of the a's is divergent, let me separate these. That means the smaller of the two sums is infinite, has an infinite value, then the bigger sum also has to have an infinite value. So the summation of the b's must be divergent. Okay, so to use, we'll do a few examples of this, but there's a few possible mistakes you can make. If I know that the smaller series, the A series, is convergent, that doesn't tell me anything about the bigger series. Or if I know if I start the process and I know the bigger series is divergent, that doesn't tell me anything about the smaller series. All right, so let's do some examples. Suppose I want to analyze the series summation of 2 divided by n cubed plus 1, where n goes from 1 to infinity. And we're trying to answer the question, is this convergent or divergent? So to do a comparison, I need to come up with another series that I can make a direct comparison between this series and the new series, and that comparison needs to be in the correct direction. So let's go through it. The thought process is, so I look at this term 2 over n cubed plus 1, and I want to compare it to a simpler series, a simpler sequence that falls into one of our two categories, either a geometric series or p series. Here, you look at this, and the bottom is basically n cubed. It just has n cubed plus 1. But n cubed is the important part. So I would look at n cubed, and I'd put 2 on top just because it doesn't really matter. It's the coefficient or a constant multiplier. And so you look at these two things and ask which one is bigger. Well, the left one, the n cubed plus 1, it has a larger denominator. So if you're dividing by a bigger number, that makes your fraction smaller. So this fraction will be less than or equal to this fraction. That means that the summation of this is less than the summation of this. So now you think about this. Summation of 2 over n cubed from n equals 1 to infinity. That's basically a p series. The 2 doesn't affect anything. That's just a coefficient. If you like, you can pull the 2 out. One over n cubed, that's a p series. And p is 3, which is bigger than 1. So this is convergent. So our unknown series, this one, is less than or equal to convergent, to something that's convergent. And if you're smaller than convergent, that means you're convergent. So my answer for this series is convergent. Okay, let's do another one. Let's do the summation of 5 to the n plus 2n divided by 3 to the n. N goes from 0 to infinity. So the question is it convergent or divergent? Well, again, we look at our term, and we want to kind of figure out what kind of series is that most similar to. The rule of thumb is you kind of take the most powerful term from the top and the bottom of the fraction. So exponential stuff is more powerful than polynomial stuff. So I would guess I want to take that 5 to the n from the top and 3 to the n from the bottom, that's the same thing as 5/3 to the n. That's a geometric series, so we'll know exactly how it behaves. But then you have to ask, what's the direction? What is the comparison? Well, this one, the numerator, we're adding something. We're adding a positive number. This one doesn't have that extra plus 2n. So this one has a bigger top of the fraction. So this left fraction will be bigger this time. This is greater than or equal to this. This series, summation of 5/3 to the n, that's a divergent geometric series because r is 5/3. The absolute value of r is 5/3, which is bigger than 1, bigger than or equal to 1. So this is divergent. So our unknown series is greater than divergent. And in this context, we can think of divergent as being infinity. So bigger than infinity is also divergent. Okay, let's do one more quick example. All right, so suppose we wanted to do summation of 1 over 2n to the 5th minus 1 from 1 to infinity. So we look at this, and again, we kind of want to make it simpler by ignoring stuff. Well, this minus 1, if we go back to our first example, we might think, well, let's just ignore the minus 1 and just take the 2 into the 5th. This time, this one has a smaller denominator because we're subtracting 1 on the bottom. So if we have a smaller denominator, that makes a bigger fraction. So it goes like this. This one is bigger than this one. But this, 1 over 2n to the 5th, that's basically a p series. Again, the 2, that's just a multiplier, so we can kind of pull that out. This is a p series with p equals 5. And if p is 5, that's bigger than 1, so this would be convergent. So in our situation, our unknown series, we have established that it's bigger than something that's convergent. That doesn't tell us anything about this series because infinity is bigger than the convergent thing. So a divergent series will be bigger than a convergent series. Or you could just have a slightly bigger convergent series. So you could have a finite value that's just bigger than the finite value of this one. So bigger than convergent, that's inconclusive. It doesn't tell us anything. So that doesn't necessarily mean we're done. I could try to get more clever with my comparison, like try to compare this with something different. Like I could try to do something about that 2. Let me erase. Like probably I could argue that for large enough n, this denominator will be quite a bit bigger. 2n to the 5th minus 1 will be quite a bit bigger than n to the 5th. So in that case, for large enough n, I could get this, probably. But that would take a little bit more work. I'd have to pinpoint it for exactly what values is this not true and make sure that eventually this is always true. But that's maybe not worth it. My point with this example is sometimes the obvious comparison that to make doesn't get you to a conclusion with the ordinary comparison test. Sometimes you can try to be more clever and come up with a more complicated or less obvious comparison, but instead of doing that, let me show you the next theorem called the limit comparison test. Okay, so again, we've got two series, summation of AN and summation of BN, where AN and BN are positive. The terms of the series are positive. So I don't have a comparison between these two terms. I can't compare A and B in general. So I can't say one's bigger than the other. It might be, but it doesn't matter in this case. What I look at is the limit of their ratio. So you look at the limit of AN divided by BN. And you could do BN divided by AN. There's nothing special about either of these. I just have two separate series. I'm going to divide their terms. And then I look at the limit as n goes to infinity. If this equals a number, L, that's strictly bigger than 0, so that means I look at this limit, I don't get 0, I don't get infinity. I get some number as my answer, some positive number as my answer. It can't be negative because the AN and BN are positive. But if this is the case, then we can say it different ways. Basically, the series have the same behavior. Either they both converge or they both diverge. So either summation AN and summation BN both converge or both diverge. All right, so we'll look at an example. Let's look at the one we just got through considering. But the idea is, one of these is my unknown. Like I'm given a series AN, summation of AN. I try to find another series that looks similar to the one I'm studying, but I don't necessarily have a direct comparison. Well, I take that similar series and then I do this test. I take the limit of this ratio, and if I get a nice positive answer, then my unknown series has the same behavior as my known series. So let's do that example. Well, we'll do a few examples, but suppose I wanted to do summation of 1 over 2 into the 5th, I think I said, minus 1, as n goes from 1 to infinity. So, I want to answer the question for this. I go with my same series that I tried to compare it with last time before. That was summation of 1 over 2n. I know this one converges, which leads me to suspect that this similar one should converge, but my direct comparison didn't help me to conclude that, because this one, the unknown, was bigger than this one, and bigger than converge doesn't tell me anything. But if I instead use the limit comparison, the limit comparison test, I look at the limit as n approaches infinity of one of these divided by the other one. So we'll do 1 over 2n to the 5th minus 1 divided by 1 over 2n to the 5th. Now let's simplify that so we can find the limit. This 2n to the 5th will flip up to the top. We'll have 2n to the 5th over 2 into the 5th minus 1 as n goes to infinity. That's a rational function with the same degree on the top and the bottom, so it's just going to be, the limit's going to be the ratio of the leading coefficients, so 2 over 2, which is 1, and that's a finite answer. It's a positive finite answer. It's bigger than 0, so that tells me the unknown series has the same behavior as the known series. They both have to converge in this case. So it's a convergent series. Okay, so the limit comparison test is, in some sense, once you get the hang of it, in some sense it's easier to deal with than direct comparisons. It's more work because you have to compute a limit, but you don't have to be as careful. You don't have to make sure you get the direction correct. And that's a good thing because, let me look at another one. Sometimes, not only is it difficult to figure out the direction, but you can't really come up with a direction. So what I mean is, suppose I wanted to find I want to look at the series 5 n cubed plus 2n squared, 5n cubed plus 2n squared divided by the square root of n to the 7th plus 6 n squared plus 1. This is a very complicated expression. Let's try to figure out what is a simpler sequence that it's similar to. So, just like I said before, the rule of thumb is I want to just basically look at this fraction and pick out the most powerful part of the top and the bottom. So 5n cubed is the largest power on the top. So 5n cubed on top. On the bottom, it's all happening inside a square root, but the most powerful term is n to the 7th, so I'd have square root of n to the 7th. Now, I'll simplify that, but let's see about a direct comparison. Well, it's tricky because this one, the top is bigger on this side, so that would suggest that this is a bigger fraction than this one. But the bottom is also bigger, so I'm dividing by a larger number. That would suggest that this more complicated fraction is smaller than the other one. So I don't know which is bigger. One thing points to this side being larger, one thing points to this side being larger. So I don't really know how they compare. But I don't care how they compare if I use the limit comparison theorem. I'm just going to look at the fraction, this divided by this, and compute that limit. And if I get an answer, that tells me that these two series would have the same behavior. But before we do that, let's conclude what this series does. If I simplify, let's see, square root of n to the 7th, that's n to the 7 over 2. So if we subtract our powers, n cubed is n to the 6 over 2, so this is 5 over n to the 1/2 when I reduce. And that, as a series, will be divergent by the p-series test. P is less than 1. P is 1/2, and that's less than 1. All right, so I'm trying to compare this indirectly with the limit comparison theorem. All right, so hopefully I have enough space here, but limit of this thing divided by that thing. 5n cubed plus 2n squared divided by this square root. I can already tell this is going to be take some space. So rather than divide it. Let me take this fraction and multiply by the reciprocal of the other fraction. I guess let's take the simplified one. That'll be a little bit nicer. So if we multiply by, n to the 1/2 is square root of n. Yeah, so okay, so I'm gonna have to simplify this. I guess n to the 1/2 is a little bit easier to work with in this context. So let's simplify this. 5n cubed times n to the 1/2, that's 5 times n to the 7/2, plus 2 times n, 2 is 4/2, that's 5/2. Okay, I'm going to move this 5 in, well, I guess I don't really need to. I could square it, make it 25 and move it on the inside, but it's not really necessary. Okay, so the limit of this as n goes to infinity, this is not a rational function, but it does involve powers of n. And so you look at the degrees, the largest power of n. On the top, it's 7/2. On the bottom, we have n to the 7th, but it's inside of a square root. So it's really n to the 7/2 on the bottom as well. So it's top and bottom of the same degree. The lower degree stuff, that becomes irrelevant. So we take the ratio of 5/5 here, which is again 1. 1 is positive, so our unknown series has the same behavior as our known series, which was divergent. So our answer is divergent. So I didn't show the work here, but this is just the same trick where you to find the limit of one of these fractions, you take the largest power of n from the fraction and divide top and bottom by that power of n. So I'd be dividing everything by n to the 7/2. What's going to happen is these two n's are going to become 1. These other n's will become fractions that have n's in the denominator, and when you reduce it, only n's in the denominator, so those fractions go to 0. So the only thing left will be 5 divided by 5 square root of 1 as n goes to infinity. Okay, so that's review from way back in Calculus 1 when you did limits as x went to infinity. That was our trick at that time. Okay, so let me say just a little bit about why this works. The main thing is just knowing how to apply these comparison theorems. But let's talk about why the limit comparison theorem works, or limit comparison test, why it works. So why does the limit comparison test work? Okay, so we suppose that the limit of an over bn as n goes to infinity equals L, and L is a positive number. Then what I can do is find two other numbers. So L's not 0. So let me make a number line picture here. L is not 0, so there's space between 0 and L. So what I can do is find a number inside that space, call it m, lowercase m. And since L's not infinite, I can find a bigger number, call it capital M, that's bigger than L. So I'll write that down better, but I can find these two m's, little m and big M. find these two m's, then what I can do is, for large enough n, so I go sufficiently far out in my sequences, this fraction, an over bn, has to get arbitrarily close to L. It has to get closer and closer to L. So eventually, it's going to be between these two m's. So an over bn will be between, it'll be close to L, so it'll be between little m and big M. Well, now I've got this compound inequality I can work with. Let's multiply everything by bn. Then what I get are bounds on an, or an is trapped between two different sequences involving bn. So now think, what happens if bn converges? If the summation of bn converges, then if I multiply it by capital M, that'll also be a convergent series. So then capital M, Bn will be a convergent series. But then we can use a regular type of comparison test to conclude that the series of ANs, the summation of ANs, converges. That's just by an ordinary comparison. So that says if Bn converges, An converges. If An converges, if we knew for a fact that An converges, then little m Bn also converges because it's smaller than An. But then I can just divide that series by little m, and I can say that summation of Bn's converge. So if one of these two converges, the other one has to converge. If we do the same thing for divergent, if we assume that Bn is a convergent, let me say that again. If we assume that the summation of Bn's is a divergent series, then that means the summation of little m Bn is a divergent series. And since the a's are bigger than that, that would have to be a divergent series. And finally, if we knew that the summation of An's diverge, well, this capital M Bn series would also have to diverge. So we could divide by capital M. And, well, that's a little bit more trickier logic to write out. But we could conclude then that if capital M Bn is a divergent series, we could conclude that the summation of just the b's has to be divergent. I won't go through it, but we can get all possible combinations out of this pair of inequalities. So the conclusion then is, if we're able to do this, that means the two series, the summation of ANs and the summation of BNs, have to have the same behavior as far as convergence or divergence goes. If one converges, the other one has to converge, and same for diverge. All right. So these take practice. I will put up a list of problems when at the end of this video.